This is Facility Science Podcast number 8. I am Jason Doolittle, and today I'm talking about power distribution inside buildings. And you might want to, if you haven't yet, go back and listen to podcast number 6. That's where I talk about basic electricity and power, because I'll be using some terms that I define in that particular episode. And I'm in the US, so I'm going to talk about the voltages and some terminology that we use in the US for electricity and power distribution, because it's what I'm most familiar with. And so the exact details might be different for other parts of the world, but electricity works the same everywhere. So the concepts will apply universally, even though you might have different numbers for voltages or whatever. So first I want to talk about some voltage classifications. So we talk about voltage by describing it as high voltage or low voltage or medium voltage often. And so low voltage in this particular context is anything up to either 600 volts or 1,000 volts, depending on which standard you look at and when. And this is the voltage that we use inside of buildings to power our devices and appliances. And, from our point of view, inside the building, 1,000 volts certainly seems like a high voltage, but it's at the low end from the point of view of the power distribution industry. And then beyond low voltage, so anything above 1,000 volts up to, again, depends on which standard you look at, anything up to maybe 60,000 volts, something like that, would be considered medium voltage. And then anything above that, we call high voltage. And high voltage is used for long-range transmission of power. And then we use medium voltage or high voltage, depending on how we want to call it, for distribution in local areas. And then we use the low voltage, like I said, inside the buildings. And we use the high voltage for long-range transmission because with a higher voltage, we can use less current to deliver the same amount of power. And power is voltage times current, so higher voltage, less current. And the reason why that's important is because a high current causes more energy loss in the transmission line due to heating. So the lower we can get the current in the long-range transmission line, the less energy we'll be wasting just sort of carrying it along that wire a long distance. And then we use the low voltage inside of buildings because it's safer and it's easier to manage at the scale of appliances and human interaction. In most places, utilities transmit and distribute a three-phase alternating current. And I'll cover the details of three-phase power probably on a later episode, unless you're listening from the future, where I already did that, in which case I already covered this in whatever number that was. Okay, so electrical power is generally distributed as alternating current at, that's usually 60 hertz in North America, so 60 cycles per second back and forth, or 50 hertz in Europe and other places, depends on sort of the origins of their electric system, which frequency they use for their power. And again, before I get into the building, let's talk about a transformer. This is an important concept to understand. A transformer, for our purposes here, is a device that we use to convert from one voltage to another. And a transformer uses what's called inductance to accomplish the conversion. So what does that mean exactly? So when a charged particle travels through a wire, which is another way of saying that when electrical current flows through a wire, it creates a magnetic field around the wire. And that magnetic field can act on things that are near the wire. And the strength of the magnetic field is proportional to the current flowing in the wire. Now, a magnetic field that changes the strength over time, so a changing magnetic field, will create a voltage in something near it. And a voltage will cause current to flow. We happen to distribute our power using alternating current, which means that the current constantly changes directions so that it's flowing first one way and then the other way. And this means that AC, alternating current, by creating a constantly changing magnetic field, will induce a current, an alternating current, in a nearby wire, assuming that that nearby wire is part of a circuit in which current can flow. So a transformer takes advantage of this phenomenon. And so it's made up of two coils of wire, which aren't touching each other. And a coil is just what it sounds like. It's wire wrapped around and around and around. And the wire is wrapped around a core that has a high magnetic permeability, which just means that it transmits the effects of a magnetic field very well. And the two coils and the core are arranged in a relationship to each other to maximize the effects of the inductance. And I hope you're still following me here. So what this means is you connect one voltage to one coil in the transformer. The alternating current flows back and forth through that coil, which induces a current in the other coil, and if that coil is connected to a circuit that creates a return path all the way back to the other end of the coil, you'll get a current flowing through that other circuit proportional to the current that's flowing through the side that you connected your input on. And the amount of voltage that's induced is proportional to the number of turns or number of windings in the coil. And so you can have a certain number of windings on one coil and a different number of windings on the other coil. And so the voltage on the one side will induce a different voltage in the other coil. So and that's proportional, and you can calculate what voltage you'll get given your input and the number of turns you have on each coil. And it turns out that these magnetic fields, these inductance fields, they interact with each other, so that when the input coil is inducing voltage on the output coil, the amount of current that will flow through the input coil is exactly the amount of current you need to induce the current flow in the other side to feed all the loads in the circuit. It just works out that way, the magic of electromagnetic fields. And so some terminology here, when we talk about these coils in the transformer, we talk about the primary and the secondary. And the primary is the part where we connect the input voltage, the voltage we're converting from, and it's usually the higher voltage, but not necessarily. And then the secondary of the transformer is the part where we connect to get the output voltage, or the voltage that we're converting to. So primary and secondary. So this is just a device that we use. We use some properties of magnetic fields and electricity to convert from one voltage to another voltage. All right, so now how do we actually get into the premises of the building? So the building itself, or the facility, campus, whatever, is connected to a medium or low voltage utility line, depending on the power requirements of the site and its proximity to other buildings. Almost always low voltage, so under 600 volts, and only medium voltage for facilities where with very high power requirements. And it's typical in a dense residential area for a low voltage feed to serve multiple lots. In a more sparsely populated area, or in a commercial or industrial area, it's typical for the utility to bring a medium voltage line to the premises, so to where the building is, and then convert to the proper voltage for that facility, usually low voltage, with a transformer very close or adjacent to the site or on the site. And most often, this transformer is owned and operated by the utility, but sometimes can belong to the building. So basically what this means is, if you have a building, the power lines on the pole will come, not always on the pole, sometimes they come from underground, but they'll come and they'll be 10,000 to 20,000 volts at the pole. They'll connect to a transformer, which will convert to whatever voltage is used in that facility. And a transformer, usually if you look up on the pole, it looks like a big trash can, a big cylindrical device, or it could be a rectangular, like a box, or it could be, and they're usually gray or white when they're up on the pole. It could also be a box, a big steel box sitting on the ground on a concrete pad. For some reason, where I'm from, they're always green when they're outside. Or it could be a gray, usually for some reason they're always gray when they're inside, a gray box sitting inside a room in the building. And I'm going to, like I said before, I'm going to describe the typical connections used in the U.S. because that's what I'm the most familiar with. So a residential or a light commercial building in the U.S. will usually be connected in a split phase, 3-wire configuration. So the secondary side of the transformer, the utility transformer that's going to feed the building, the low voltage side, is 240 volts, so across the secondary coil. And with a grounded neutral connected at the center of the secondary winding. And the customer gets both conductors from the secondary side of the transformer, so that's 240 volts AC between them, and also the neutral, which means they can also use 120 volts AC from the neutral to each of the other two lines. So most of the loads, the lighting, the wall receptacles, etc., use the 120 volt AC from the neutral to one of the two lines, and then the 240 volts, so connect across both lines and not the neutral, is typically used for higher power loads such as water heaters, HVAC equipment, clothes dryers, ovens, large power tools, things like that, things that use a lot of power. And so 120 volts AC in the US is the typical plug load voltage in a house or a office or whatever. And then commercial or industrial buildings are typically connected with three-phase systems. And in the US, this is typically either a 208 three-phase, so it's 208 from phase to phase, or 120 volts from phase to neutral, or it's 480, 277, and rarely some others. And this is usually 4 wires that get delivered to the facility from the transformer, from the utility transformer, and that's one for each phase line and a neutral. That's the fourth one. So a 208, 120 three-phase means that you get 120 volts AC between any of the 3 lines and the neutral, and then you get 208 volts between any 2 of the 3-phase lines. And then you can also use all 3 lines to get 3-phase 208 volts. And again, I don't want to go too deep into 3-phase here. I'll cover that on a later episode. And then, like I said also before, electrical service comes to the building either off of a pole or underground, passing through the transformer, and then it'll pass through an electric meter before entering the main panel or switchgear inside the building. And the electric meter is usually located outside, but in most areas can also be located inside a room, as long as that room satisfies certain conditions that are suitable for the utility. And the general requirements for electric meter installation location is that it must be easily accessible by both the electric utility service personnel, so they can come service the electrical service if necessary, and also the utility customer, so that might be the property occupant or basically the person paying the bills. And the meter also has to be installed in such ways to allow space and conditions for safe work. And this is called power distribution inside buildings. I've been going on for a while and we haven't gotten inside the building yet. So after passing through the electric meter, the electric service will then enter the building and land on some sort of distribution device. All right, so the simplest case of a small building fed with a split phase 120 240 volt system or a 3-phase 208 system, there might be just a single panel board. It's a breaker panel, electric panel, a load center, whatever you want to call it. This thing is filled with circuit breakers that serve the branch circuits in the building. And this is what you'd commonly find in a small office or storage building or a single family home. So the electric service comes in, hits the meter, and then hits the only one panel, one distribution device in the building, and that's what you got. And I said branch circuit. A branch circuit is a circuit that provides power to devices in the building, such as light fixtures and plug loads and appliances. And the circuit breakers for branch circuits are sized appropriately for the expected load. So typically in the US, a lighting or wall receptacle circuit are 15 or 20 amps, and then circuits dedicated to appliances are sized appropriately for that appliance, so ovens or air conditioning equipment or whatever. And these electrical panels are laid out so that adjacent breakers are on different phases. So in a 3-phase panel, for example, if you call the phases A, B, and C, a breaker connected to phase B will have an A phase breaker above it and a C phase breaker below it. And similarly, in a split phase system, so a 240-120 system, the breakers will alternate between each side of the split phase. And this is done so that you can use multiple phases to power a high power appliance. So a 2-pole breaker can be installed anywhere in a split phase or a 3-phase panel and be guaranteed to contact 2 different phases. And similarly, a 3-pole breaker can be installed anywhere in a 3-phase panel and be guaranteed to contact all 3 phases and not contact any single phase more than once. Now, in addition to the circuit breakers that serve the branch circuits, The panel will likely include a main circuit breaker that will allow disconnection of the entire panel from the electric service. And this breaker will be sized to serve the entire load of all the branch circuits served by that panel, possibly up to several hundred amps. And if more than one panel is necessary, so maybe you need 2 or maybe 3, it's common to install additional panels near the first one and then just feed them from circuit breakers in the first panel, assuming the service is sized appropriately to accommodate that power consumption. Now, if you move into a larger building, it's a building with multiple electrical rooms, for example, it's spread out over a larger area. The utility service might first connect at a distribution panel intended only just to feed other panels. This is often called a switchboard or sometimes switchgear, though the term switchgear is generally reserved for higher voltage distribution. And there might be a feed from this main panel to each electrical room in the building if there's multiple electrical rooms. And the connection from this main panel to other panels are called feeders as opposed to branch circuits. So these are feeder circuits. And the connection coming off the main distribution panel, so to the other electrical rooms, to the other panels, will be protected by an appropriately sized circuit breaker, potentially, but not necessarily, eliminating the need for a main circuit breaker in the other panel, depending on the layout. Now, buildings served with a higher than the standard plug load voltage, so higher than the 240 120 or the 208 120, some buildings are served with a higher voltage. And in the US, this is usually 480 three-phase, or sometimes 600, but usually 480. And with 480, that 480 is the phase-to-phase voltage in a three-phase 480 system. 270 is the phase to neutral. So you get the same 4 wires, 3 phases and a neutral, 480 from one phase to the other phase, and 277 from each phase to the neutral. And this is for larger buildings or buildings with higher power requirements. So a building with a 480 three-phase setup will generally use the 480 voltage for higher power loads such as air conditioning and heating and pumping and things like that. And it's also common to use the higher voltage for lighting, and usually it's 277 volts for the lighting. You can power about twice as many light fixtures with the same number of circuits and wire and conduit and etc. So that's why you would use the 277 to power the lights. And of course, you'll still need the 208 120 for the regular office equipment. So a building like this will have transformers inside the building. In addition to the one outside that the utility services, you'll have transformers inside the building that step the voltage down to the regular line voltage in order to make that 120 volts available, or the 208 that you might need to service appliances. So in a typical facility, the 408 volts service will enter the building and land on some type of switchboard. And some people might call this the main switchgear. Others reserve the term switchgear for medium voltage and higher, but you'll probably hear both a switchboard or switchgear. And the switchboard will likely include, not surprisingly, a disconnecting device, probably a circuit breaker, maybe even a remotely operable circuit breaker that will allow disconnection of utility power. And from this switchboard, power will be distributed to all the other electrical rooms or electrical distribution spots in the building. And generally, the power will be distributed across the building at the higher voltage. So what we're talking about here is the 480, 277. That's the voltage we'll distribute to all the electrical rooms. And then at each electrical room or otherwise distribution space, the 480 lines will enter a switchboard. There's another switchboard. And the switchboard will then feed the distribution devices in that electrical room, usually, again, through a circuit breaker sized appropriately for the downstream load. Power will generally be distributed throughout the building at the higher voltage, both because we want to be able to power high power equipment and lighting at each part of the building, and also because we can minimize the power losses in the feeder lines. And I'm not sure if I covered this concept of line losses really before, so I'll do it now. When current travels around a circuit, it consumes all of its potential energy, which means it drops all the voltage. So, in a conceptually simple case, if it starts out with 120 volts, it travels through the circuit and it gets back to the beginning with 0 volts. So it has to use all 20 volts in the circuit. Now, ideally, energy is only consumed in the devices we intend to power. But in real life, the wires themselves consume some energy by warming up from all the electrons traveling through them. So if the wire run to a device is really long, a device on a 120 volt circuit might only see 115 volts on the wire because 5 volts were consumed by the wire. And the amount of loss is proportional to the current traveling through the wire. So higher current means more loss, more voltage drop. And since power is voltage times current, I've said that a couple times already, a higher voltage means lower current, which means less power consumed in the wires, right? So that's one of the reasons we choose to distribute power at the highest available voltage when we're going across our building. Okay, so at each electrical room, we'll have a panel to serve the higher power loads in that area, so the air conditioning or whatever else is in the area, with the 480 or 277 volt power. And this might be the same switchboard the power lands on in the room. And it's also typical to have in a 480 building, a 277 volt panel for lighting. And then the switchboard will also power a transformer to convert from the 480 down to the 208 to get the 120 for all the plug loads and the regular, office appliances and whatever else. And then if many of these 208 or 120 volt circuits are needed in this part of the building, the output of the transformer might feed a second switchboard, which will then feed multiple breaker panels, each protected by a circuit breaker of the appropriate size. And at each step of the distribution inside the facility, there will be an appropriately sized overcurrent device, a circuit breaker that I've been talking about. So the main switchgear will feed each electrical room with a circuit breaker size to accommodate every load served from that electrical room. And then the switchboard in each electrical room will feed the step-down transformer with a breaker size to accommodate every load served by the transformer. And then the switchboard fed by the transformer will supply every panel connected to it with a breaker size appropriately for the loads at each panel. And finally, each branch circuit in each panel will be supplied through a circuit breaker appropriately sized for the load on that circuit. And so what this means basically is that a fault at any stage in the distribution network will ideally, hopefully if everything's working correctly, trip the nearest upstream circuit breaker without taking down the whole building. And also the placement of these circuit breakers at each stage will prevent, hopefully, creating a dangerous situation on an inadequately protected connection. Okay, now some facilities use a lot more power than can be reasonably provided at 480 volts or 600 volts. And so these buildings can be fed by the utility directly from the medium voltage distribution lines. And this will be in the neighborhood of 10 to 60,000 volts or 10 to 60 kilovolts. And this is things like high-rise buildings, large campuses, or certain kinds of industrial facilities. And these facilities will have a substation or potentially multiple substations on premises to convert to the usable voltages, the voltages they actually want to serve their loads, and distribute it throughout the facility. So in some cases, the facility will use the medium voltage directly. So this is true in the case of some industrial facilities or large pumping stations or things like that. In some cases, the medium voltage will be distributed to substations at key points in the facility and then converted to the 480 and the 208 in the typical configuration and used for the typical loads that I described before. And this is especially true for like a large campus or a skyscraper, a large high-rise building. And then in other cases, there might be a single substation in the building that converts to the facility's usable voltage, and then all the voltage will be distributed at the low utilization voltage, the 480 or 600 or 208 or whatever. And this would be the case for some high-rise buildings, or also for buildings with a very high density of low voltage equipment, such as a large manufacturing facility or a very large data center. And remember, I'm using the low voltage here to describe anything under about 1,000 volts or 600 volts. Okay, now I've talked a lot about voltages in transformers and switchboards and stuff like that, but I haven't really talked about the actual conductors that carry the electricity across the facilities and to the devices and appliances. So I'm talking about wires here, right? The long, skinny pieces of metal, usually made of copper or aluminum, and sometimes a conductor or a wire is a solid piece of metal, and sometimes it's made up of many individual strands twisted together. And the metal conductors are usually insulated with a plastic of a type and of a thickness that's appropriate for the voltage that's going to be put on the wire and the environment the cable or wire is going to be living in. The amount of current a conductor can carry is dictated by its size. So that's its cross-sectional area, or similarly its diameter for a round cable. So a larger conductor can carry more current than a small one. And if a conductor carries too much current, it will heat up and it potentially cause a fire or melt. The current carrying capacity of a conductor is called its ampacity. So that's for amp capacity, ampacity. The voltage doesn't affect how much current a particularly sized conductor can carry, right? So a conductor can carry its rated current at any voltage. Instead, the voltage affects the type and thickness of the insulation and the amount of space required between conductors, which is why you'll see on the power lines, the power lines that travel around your neighborhood, they're at the medium voltage at 10 or 20,000 volts or something in that neighborhood, and they're relatively close together. They're not touching each other, but they're kind of close together. Whereas if you go out, in the country somewhere and you see the massive steel towers that have the big high voltage lines on them, those are separated way apart from each other because they have a much higher voltage. I'm getting sidetracked with that here. So the conductors have to be protected from damage and accidental contact. So they usually run inside of a raceway or a conduit, so they can't be hit with stuff or people can't access them. And this is typically a pipe made out of steel or plastic, but it could be other things as well. And a raceway in general can only be filled to a certain percentage of its capacity to allow for proper dissipation of heat generated by the current flowing in the wires, because I was saying that current flowing through the wires causes them to heat up, and that heat has to be able to dissipate. And so we only pack our conduits so much. And some conductors aren't running conduits at all, but are instead bundled into cables. And so, say the cables are protected by some kind of sheathing, typically metal, steel, or aluminum, or plastic or rubber. And you might have heard terms like MC cable. MC is for metal clad. Romex, that's a brand of plastic sheathed cable that's typically used in residential construction. Or SO cord or SJ cord, and that's a rubber clad cable. And cables aren't run in conduit, so they have to be supported either by strapping them to an appropriate surface or running them in cable trays or similar. And there's a practical limit to the size of an electrical wire that can be used inside a building, because an individual wire has to be able to be bent and pulled through conduit and pulled into enclosures and secured to terminals. And these things are made out of metal, and so the bigger they are, the harder they are to handle. And so when the current requirements get very high, we start to use multiple conductors rather than continually increasing the size of the conductors. And the largest sort of flexible conductors in general use can carry in the range of hundreds of amps, so 400 to 600. Anything above that, you can't use a single conductor. You have to either use multiple conductors or find another method. And one of those other methods is what's called a bus bar system or a bus bar trunking system. So in some facilities with high power requirements, we use a bus bar system like this. And so rather than flexible cables, a bus bar is a rigid piece of conductive metal, usually aluminum or copper. It's what it sounds like. It's a bar of metal. And bus bars can either be individual conductors, or they can be multiple conductors bundled together as an assembly. So the multiple conductors might be like one for each phase and a neutral and a ground. The typical distribution circuit can be bundled together in one assembly. And bus bars are used when we want to move a lot of power at a high current, so up to several thousand amps. And since they're self-supporting and they don't need to bend, they can be made much larger than wires or cables. And in this case, larger means that they can be made with a higher ampacity. And bus bars typically have provisions to allow tapping into the bus bar at regular intervals, often without the need to de-energize the bus bar. And this allows for flexible reconfiguration in certain situations. These types of systems, bus bar systems, are typically used in factories, high-rise buildings, data centers, things like that. And to illustrate the benefit of this, imagine if you need to send, say, 3,000 amps up 50 floors in a tall building. Doing this, say, with copper cable would require probably 30-ish separate conductors. and all the conduit and the support structures to support all the weight of this cable. Or you could use one bus bar assembly, which can carry the entire 3000 amps in one set of conductors and then has its built-in support structure. And then additionally at each floor, passed by the bus bar, devices could be clamped to the bus bar to draw power from it. And this could be reconfigured much more easily than, say, separate conductors inside of a conduit. So you'd have to run another conductor or cut the conduit and do a splice or whatever. And so you can probably imagine how the same kind of flexible configuration benefit would be useful in a dense data center or something like a manufacturing facility. Why do we use different voltages in different buildings? What dictates the choice? And there are two main things which are actually kind of related to each other, but there are two main things. The first one might be the most obvious. You'll want to get the voltage required by the highest demand device to be used at the facility. So kind of an extreme example, if you have a steel foundry that has an arc furnace that requires 50,000 volts as its input, well, we might as well feed that facility with the medium voltage and then step down from there for whatever else they need. But even in the simple case of, a residential home, the highest power draw items you're going to have in a building like that, or maybe a water heater or an air conditioner, and a small water heater and a small air conditioner, relatively speaking. And so serving that with the lowest voltage is appropriate. In another building where you might have a large air conditioning or a large lighting loads or something like that, even in a relatively small building, you might still have sort of commercial or industrial sized equipment. So you want to feed that with the 480, 277 volt system because that equipment requires that kind of voltage. And then the other reason, which is kind of the same reason again, has to do with ampacity. Like I was saying before, the individual conductors can only carry so much current. And so if you want to deliver a certain amount of power to a building, you have to bring in enough conductors to deliver that much power. And so for, like I said, a single family, say residential house, you can deliver one cable at 240, 120 split phase to the house, and that'll be plenty of power to power everything in the house, no problem. For a bigger building, one cable is not going to do it. So you have to use 2 or 3 or 4. And then eventually you get to the point where, well, maybe it's not really feasible to bring so many conductors in at 208 volts 3-phase. So if we bump it up to 277 or to 480 volts, we can half the number of conductors that we need, right? And to go to an extreme case, imagine a high-rise building. That high-rise building might need 30 megawatts, right? And so we can deliver 30 megawatts at 480 volts. So round up 480 to 500 just to make the math easier. And we might need something like 100, big fat copper conductors to deliver our 30 megawatts to that building. Probably more than 100. I don't think my math was quite right there, but a lot of conductors. Whereas if we use Instead of bringing 500 volts, 480 volts to that building, we bring 10,000 volts into that building. Now all of a sudden we only need a 20th of that, or some. Again, I don't think my math is right, but some very small fraction of the amount of actual wires and conductors and area of penetration into the building and space taken up by all the switchgear that we need to land all these conductors on. Instead, we can minimize the amount of conductors by bringing in a higher voltage into the building, and then we can distribute from inside as appropriate. Okay, so I think that's all I have to say about this topic. My notes for this can be found at facilityscience.com, and this is number 8. If you have any questions about this topic or comments or suggestions for other topics you'd like to hear about, you can contact me by email at podcast@facilityscience.com. And I hope this was helpful to you. So thanks for listening.